Okay, so welcome everyone. It's my pleasure to introduce Oscar Garcia Prada, who's from ISEMAT, which is the Mathematical Sciences Center in CSIC, the Research Council in Spain. And he's going to speak to us on Higgs bundle and higher Teichmuller spaces.
Thank you very much, Jesus, and thank you for the invitation to you and to Ivan Chelsov. It's a pleasure for me to speak in this very nice seminar. So let me tell you about the objects that I'm going to talk about. So I will start with, I'm going to take this off. I'm going to start with an oriented to smooth compact surface of genus G bigger than 1. And then I consider its fundamental group, right? Then next character in this story is a real form of a complex semisimple Lie group. By real form, I mean the fixed points of an anti-holomorphic involution. And I want to emphasize that actually any complex semisimple Lie group can be viewed as a real form of the double of it. So I can take G cross G and define an anti-holomorphic involution, and G complex appears as fixed points. So the story I'm going to tell is not just about, say, real forms of a fixed complex group, not just only real groups, but is actually also complex groups, right? So in other words, GR could be complex. And so we're interested in considering representations of the fundamental group of S in GR. This is simply a homomorphism. And in order to have a nice moduli space, a nice space parametrizing equivalence classes of representations, we need to restrict to representations that are reductive. And one definition of this is if you postcompose the representation rho with the adjoint representation into the Lie algebra of GR, then that decomposes in a sum of irreducible representations. Right? So then we consider the set of all reductive representations, and we define the moduli space of representations of the fundamental group of S in GR, sometimes also refer to it as GR character variety of S, as the orbit space of considering these reductive homomorphisms and quotienting by conjugation, the action on representations by conjugating by an element of GR. Right? So this variety here is, in general, is an analytic variety, and in fact, if the group GR is algebraic, then it's an algebraic variety. And also, if the group GR is complex, this is a complex algebraic variety. Okay. So, so there is a way of assigning an invariant, a topological invariant to a representation of the fundamental group in GR. And one way to do that is by realizing this classical result that equivalence classes of representations of the fundamental group of S in GR are in bijection with isomorphic classes of flat GR bundles, or if you prefer, GR bundles, principal bundles with a flat connection, right? And so if assume that GR is connected, right? There is a story also when the GR is non-connected, but let's assume that GR is connected, then flat GR bundles are topologically classified by the fundamental group of GR. And so we can then associate a topological invariant to a representation by considering this element in the fundamental class of, in the fundamental group of GR of the corresponding flat bundle that I called E sub rho, right? That you construct out of the representation. And so then we can then fix in the character variety RSGR, we can fix this invariant, this element in pi1 of GR and consider the subvariety RC inside here, just by fixing this topological invariant. So if GR is compact, actually, if GR is compact, by the way, you don't need to, so every representation is reductive. And then you're not, you're considering all representations. You're not throwing away anything. And, but in any case, if the group GR is compact or complex, then the connected components, topological components, connected components of this Moduli space R SGR is indeed parameterized by the pi1 of GR. So once you fix the topological class, then this defines, this determines the components. There's a bijection between components, connected components of the Moduli space and elements in the fundamental group of GR. This happens when, first of all, GR is connected, right? And is compact or complex. Now, the situation is very different if you consider a non-compact real Lie group that is non-complex, right? And this is actually the main interest in our talk. This is what will relate to higher Teichmüller theory. And in general, the map that you have from the set of connected components to pi1 of GR is neither injective nor surjective. So there's both reasons to violate this bijection. And the first, most elementary and very fundamental example to consider is that of SL2R. Considering SL2R, it's a real form of SL2C, right? And in this situation, you see the maximal compact subgroup. The maximal compact subgroup of SL2R is SO2. So that's a circle. And so the topological invariant is an integer, which is referred as the Euler number, right? And so we can consider in the character variety in SL2R, fixing the Euler number and consider the subvariety RD, right? So many, many years ago, Milner proved that indeed this variety is empty unless the Euler number is bounded in absolute value by the genus of the Riemann surface of the surface -1. There is no Riemann surface structure so far, huh? So this is on the topological surface. And this of course is telling us that beyond this value, the character variety is empty. So subjectivity is violated, obviously. But then later on, several years later, like 30 years later, Goldman and Hitchin actually showed, using different methods, that if the value of the Euler number is strictly smaller than G-1 in absolute value, then this variety is connected. But if you take the maximal value, this G-1, then there are 2 to the 2G connected components in RT. So in other words, the map that I was mentioning before is obviously not injective either. Okay. So, but somehow more importantly, or say more to the point of my talk, if you want, except that is also very relevant in the subject of my talk, I want to emphasize that the maximal, the character variety for maximal value of the Euler number, of which we have said that has 2 to the 2G components, each of these components, from the point of view, so each of these components consists entirely of Fuchsian representations of the fundamental group. That is, these are representations that are discrete and faithful, and then this can be identified with the Teichmüller space of the surface. Teichmüller space that parameterizes complex structures on the surface. This was realized by Goldman. And there are, of course, other ways of viewing tabular space as hyperbolic structures or conformal structures, but whatever is your favorite way of looking at tabular space, the thing is that this component, actually, if you think of it as parametrizing hyperbolic structures, this representation that you obtained is nothing but the holonomy of this hyperbolic structure. And so the important thing is that this representation is discrete and faithful, right? So the question that we want to address is whether there are other simple groups with similar features to those of SL2R. In other words, whether we can find other simple groups for which the moduli space has connected components that are not distinguished by the primary topological invariant. The primary topological invariant being the one that I just defined in pi1 of G, of GR, and consisting entirely of discrete and faithful representations. This is the question. And over the years, say for the last, say, starting 30 years ago, two classes of groups have been identified having this sort of properties. On the one hand, the split real groups, and on the other hand, the non-compact Hermitian groups of tube type. I will define these things. So I want to address then this question and to talk to you about these two classes of groups from the point of view of complex algebraic geometry, right? I think people in this seminar will be happy about that, hopefully. And so in other words, using the theory of Higgs bundles. And so to do that, I put a complex structure on my surface S and making it a compact Riemann surface that I rename as X, right? And then, so as I said, we have a complex semi-simple Lie group and we have a real form. Now, to define a Higgs bundle in this setup, I need to consider a maximal compact subgroup of GR, right? So choose a maximal compact subgroup of GR. And once I have chosen this maximal compact subgroup of GR, then I have a whole package that is given by Cartan that tells me that on the Lie algebra of this real group, I can decompose it as the Lie algebra of the maximal compact subgroup HR, and then another piece which actually is such that this is a orthogonal decomposition with respect to the killing form that I have in GR. And this decomposition satisfies this very familiar properties in what are called symmetric pairs, right? So HR is, of course, a subalgebra, is a Lie subalgebra. MR is not, it's just an ideal, right? So, and in fact, this property here that we have here can be somehow lifted to the group. And if you want, if you consider the adjoint representation of the group GR in its Lie algebra, and you restrict it to the group HR, right? Then that breaks into two representations, precisely. These two are two representations of HR. This is, of course, the adjoint representation of the group HR. And this is sometimes referred as the isotropy representation. So you just get another representation, MR. So MR is the representation space for the group HR. And in the theory of Higgs bundles, you need to consider the complexification of that, representation. So we have a representation from H into a GL of M, this vector space M. Okay, so these are, so you have a real group. I summarize GR, you choose a maximal compact, and once you have chosen a maximal compact, you have this decomposition And in particular, you have this representation, right, of H into the complexification of MR. And these are the ingredients. I will come back if you need, because it's easy to forget all this notation. But let me now go on and define you what is what I will call a GR Higgs bundle on the Riemann surface. So this is a pair, Phi, that consists of a holomorphic principal H bundle, E, and phi is now a holomorphic section of the bundle associated to the representation. So E is an H bundle, and EM denotes here the bundle associated to the representation in M. So this is a vector bundle with fiber M. And then I tensor with the canonical line bundle of the Riemann surface. So it's a section of this bundle here. Yeah. So let me just notice that actually, if the group GR was complex, right, then you recover actually the complexification of H is itself, right, and this is just the adjoint representation, and you recover the say the notion given by Hitchin of a Higgs bundle for a complex group, say a complex group G, which is a G bundle, and a section. Phi is a holomorphic section of the adjoint bundle tensor with the canonical, right? So this is a more general setup than that one. Now, so there are appropriate notions of stability and semi-stability and polystability, so that one can consider a moduli space of, say, polystable GR Higgs bundles as the set of isomorphism classes of polystable GR Higgs bundles. I'm sure many of you here are familiar with notions of stability for vector bundles in particular, and so there are similar conditions that allow us to construct these moduli spaces. And in fact, there are constructions, algebraic constructions of these moduli spaces using, for example, geometric invariant theory. So there are here some constructions in terms of sort of degree of generality. So the key point here is that this moduli space of polystable Higgs bundles is related to the moduli space of representations, right, by the so-called non-abelian Hodge correspondence theorem. And so if S is my smooth compact surface, and now I choose a complex structure in S, it doesn't matter which complex structure you choose, then you get this Riemann surface, and the statement of the non-abelian Hodge correspondence is that there exists a homeomorphism between the character variety here, representations of the fundamental group of S in GR, and the moduli space of polystable GR Higgs bundles. And of course, I mean, this one can devote a whole seminar to speak about this correspondence, but let me just say that the proof of this, just few words, saying that is a combination of two existence theorems for some nonlinear PDEs. And one of the theorems is proving the existence of solutions to the Hitchin equations on a polystable Higgs bundle. And by that, one means a reduction of the structure group of the H bundle to HR. So like if GR was, for example, SLNC, then this is a reduction to SUN, right? So it's a Hermitian metric on the vector bundle. And this was proved by Hitchin in his original seminal paper in 1987 for SL2C, and then Simpson gave a proof for any complex group, and actually in higher dimensions. And a proof of this existence of solutions to the Hitchin equations in this generality that I'm explaining today for real groups is with my collaborators Steve Bratlow and Peter Gotten and Ignacy Mundet in a couple two different papers. So the other theorem that one needs to prove is about existence of harmonic metrics on flat GR bundles. And this is in the other side of the correspondence. If you have a representation in the fundamental group, you have a flat bundle, you just need to solve for some twisted harmonic map from S to the symmetric space defined by GR. And this was provided in the case of SL to C by Donaldson in a companion paper to the one of Hitchins, and then in general by Corlett and the other proofs also. So this is the non-abelian Hodge correspondence. And from the point of view of Higgs bundles, there is also a natural topological invariant attached. And this topological invariant attached to GR Higgs bundle is the topological invariant of the H bundle. So it's a principal H bundle. And so principal H bundles on a surface are parameterized by the fundamental group of H. But you see H is the complexification of HR, and so it retracts into HR, and so the fundamental group of H and that of HR are the same. And in fact, the relation to GR is that GR also retracts into HR, and that's why the invariant we are defining here for Higgs bundles, which is the topological invariant of the bundle, an element in the fundamental group of HR, is actually the same as you will see that appears in the appeared previously. So, but defining this invariant, we can consider the subvariety of the Moduli space of Higgs bundles, fixing this invariant C. And as I just said, this invariance from the perspective of representations of the fundamental group and from the perspective of Higgs bundles is the same, and is not surprised that the corresponding subvarieties, the non-abelian Hodge correspondence, actually restricts to give a homeomorphism of the corresponding subvarieties that one has fixing this invariant. Okay. All right. So our way of attacking the problem of topological, sort of obtaining these topological components with special properties and so on, is by exploiting this homeomorphism and now looking at really the Moduli space of Higgs bundles, that for which we have the methods of algebraic geometry and complex analysis like Morse theory and other tools. And so let me explain the first family of groups for which, as I said before, similar components to the Teichmüller component in the case of SL2R were identified. In fact, this is the beginning, if you want, of the theory, that new theory of higher Teichmüller, the new higher Teichmüller theory. So it starts really with this work here. And so GR, a split real form, is one, there are several definitions, but one in which you can find, when you consider the Cartan decomposition, you can find a maximal abelian subalgebra of GR entirely contained in MR. So, also another sort of more folkloric definition is the less compact of real forms, right? And for the classical groups, this you have for SL and C, you have SL and R. For the complex symplectic group, you have SP2 and R. And then for the orthogonal groups, you have SON, N, or SON, N plus 1. These are examples of, in the classical groups, of split real forms. And so let me explain what happens for the particular case of SL and R. And in fact, to explain what happens for the case of SL and R, I need to consider SL and C, and to remind you that there is if you consider the group SL and C and its algebra, SL and C, so the invariant polynomials, you can find a basis for the invariant polynomials of the action of SL and C in its Lie algebra. And these are provided by the coefficients of the characteristic polynomial of a trace-free matrix, A, an element in this Lie algebra, right? So these characteristic polynomials are a basis, a particular basis for the algebra of invariant polynomials of SL and C, and with degree of pi given by I plus 1. And so now you can define, this is a very important aspect of the theory of Higgs bundles, what is called the Hitchin map, from the moduli space of Higgs bundles for the group SL and C. You can think, actually, I have been giving a perspective of principal bundles, but of course, if you are working with the group SL and C, and in fact, for you're working with any classical group, but in particular for SL and C, you can think of a Higgs bundle as a pair, which is a vector bundle, E, and whose determinant is trivial, and a Higgs field is now an endomorphism of E to E tensor K, a homomorphism from E to E tensor K with a null trace, right? And so I can now define a map from the moduli space of Higgs bundles by evaluating the invariant polynomials that I discussed before in phi, getting this map from the moduli space of Higgs bundles to the direct sum of these holomorphic differentials of different degrees, right? And so Hitchin, in a very important paper in 1992, constructed a section of this map, and for that he used something called the constant principal SL2. I'll come back to this, and he defined, as I say, a map from this vector space into the moduli space, and proved that that actually falls into the moduli space of Higgs bundles for SL and R. So these are representations of the fundamental group in SL and R, and in fact is a full component, So this he called at the time generalized Teichmüller component, but nowadays it's called Hitchin component. And so if you take in particular SL to R, then the Hitchin component, here there is only K squared, and so the Hitchin component is actually is given by the space of holomorphic quadratic differentials on the Riemann surface. And so this identifies the Teichmüller space of the surface with the space of quadratic differentials, right? And this is the usual Teichmüller space. So in fact, in his 1992 paper, he gives a general construction for any split real form. I just illustrated the case of SLNR, but there is a general construction. And in particular, so one can find several components, but if the group GR is of adjoint type, so there's no center, right? Then this component is essentially unique. I say essentially because sometimes there are two components that have to be identified by some outer automorphism, but it's essentially unique. And so, moreover, looking at the representations corresponding to the Higgs bundles in this component, every representation in the Hitchin component can be deformed to a representation that factors through a representation in SL2R, so like this from the fundamental group of S to SL2R and then to GR, where this representation here is actually is in the Teichmüller component of SL2R, and this embedding of SL2R is what is called the principal, is actually the principal embedding of SL2R that always exists for any split real group. In the case of SLNR, this is just the irreducible representation that one has of SL2R in SLNR, right? This is the principal representation. And so here's another pillar of the theory of Higgs bundles and in relation to representations of the fundamental group is the work of François Labourie, who in 2006 introduced the notion of anosov representations. These are bringing ideas from dynamical systems to representations of the fundamental group. And so by considering this theory, he actually proved that, well, he defined this notion of anosov representation and shows that anosov representations are actually discrete and faithful. And in particular, he shows that the Hitchin component consists entirely of anosov representations, and hence the representations in the Hitchin component are also discrete and faithful. This is what we were asking at the beginning, right? So this in very special sort of representations. So now let me consider the second class of groups, of real groups that for which similar kind of components were identified. And these are the groups of Hermitian type. And this is a bit abusive to call the group of Hermitian type. What we mean is that the symmetric space obtained by quotienting this group by its maximal compact is actually a symmetric space of Hermitian type that is admits a complex structure that is compatible with the natural Riemannian structure that one has on real symmetric spaces. And in fact, this is a Cayley manifold. These are the Hermitian symmetric spaces. So to see what we have in mind, so classical connected simple groups of Hermitian type are SUPQ, this is a real form of SL and C, the real symplectic group SP2 and R, and then SO star to N is a non-compact dual of SO to N, and this other real form of SO 2 plus NC. And two exceptional real forms. One is a real form of E6 and another a real form of E7. And notice, by the way, that SL2R actually features in the two lists. On the one hand is a split real form of SL2C, of course, so is in the first family that we just discussed, but it also appears in these lists, and actually it appears sort of in different manifestations because it is isomorphic to SU11. It's also SP2R, and in fact is locally isomorphic to SO 02,1. So in other words, SL2R is in both families. And so these were two directions in which we could generalize the story of SL2R. Now, so if GR is simple and say the torsion-free part of the fundamental group is actually isomorphic to the integers, right? And hence the topological invariant of a GR representation or a Higgs bundle for this group is also an integer. This is like in the case of SL2R. And this integer, that was the Euler number, is called here the Toledo invariant. It's an integer associated to a Higgs bundle for these groups or a representation. And an important feature here is this generalization of Milnor theorem in this setup, that the Toledo invariant in absolute value is bounded by the rank of the symmetric space times the genus -1. And so this generalizes the Milnor inequality that we just saw. We saw before for SL2R, and there are several proofs for this inequality. Say for the classical groups, in the case of the symplectic group, this goes back to Rayev and to Domich and Toledo. This in terms of representations. That now from the perspective of Higgs bundles, where these inequalities are always proved by using semi-stability, just applying semi-stability. Is the work with my collaborators, Steve Bradlow and Peter Gotten, my collaborators Bradlow and Gotten. And there is a general proof that for representations is Burger, Joseph, Winhardt, and for Higgs bundles is in collaboration with Picard and Rubio. And so the class of in this situation, what we really want to study is the maximal Toledo invariant situation. This is like in the SL2R case, the maximal Euler number. So here we are particularly interested in studying the maximal variety, the subvariety of the moduli space where the Toledo invariant is maximal. So that is in absolute value is the rank of the symmetric space times G minus 1, right? Because it is here where the action happens, okay? And the action that happens, I will explain. So what happens is that within the symmetric spaces of tube type, there is a class which is called of tube type. And what does that mean? I mean, perhaps many of you are familiar with the fact that this non-compact Hermitian symmetric spaces can be viewed as, you know, the work of sorry, the name escapes me now. Certainly for Cartan and Harishchandra. Cartan and Harishchandra in terms of bounded symmetric domains. And sometimes these bounded symmetric domains admit a biholomorphism to a domain of tube type. And this is a tube over some cone. For example, the case of SL2R, the symmetric space is the Poincaré disk, and the usual Cayley transformation identifies the Poincaré disk with the upper half plane. So the upper half plane is the tube realization. So these are Hermitian symmetric spaces for which there is something like the upper half plane. These are called of tube type, and a characterization of when a Hermitian symmetric space of non-compact type can be is biholomorphic to some tube, right, is given by some portion of the topological boundary of this bounded symmetric domain, which is called the Shilov boundary. It's some piece of this topological boundary, and generally this Shilov boundary is a compact homogeneous space, but sometimes is a symmetric space. So when it is a symmetric space, then a compact symmetric space, then you can realize this, you can find a biholomorphism of the bounded symmetric domain to this tube thing. And this is a tube over a cone, and the cone is precisely the non-compact dual of this compact symmetric space. Okay, so there is this Shilov boundary and there is this compact symmetric space, right? And so here is the theorem, that the theorem says that if GR is such that this is a Hermitian symmetric space of tube type, and let's now give a name to this is the non-compact dual of the Shilov boundary, which is a compact symmetric space. And remember, symmetric spaces, real symmetric spaces come in pairs always. So for every compact symmetric space, there is a brother, which is non-compact. This is the brother or sister, as you prefer. And so this is a non-compact dual. And the theorem says that the moduli space of GR Higgs bundles with maximal Toledo invariant is actually isomorphic to another moduli space of Higgs bundles for another group that is non-compact, is this G star R. But now, instead of the in the definition of Higgs bundle having this twisting by K, you have a twisting by K squared. So it's the same kind of object. It's an algebraic. So the theorem says this is an isomorphism of algebraic varieties, of complex algebraic varieties. The group may be real, but these are complex algebraic varieties, where the complex structure is defined by the complex structure of the group, of the curve X. And so this, so to have a precise idea what are the groups we are talking here, you know, only the SUPP, so when P and Q are equal, is of tube type, sp2nr is always of tube type, and SOS star 2n is when n is even, and then this is always of tube type, and of the exceptional domains, only the E7-1 is of tube type. And so this theorem here was proved over the years on a sort of case-by-case situation. And for the classical groups, this was my work with Steve Bradford, Peter Cotton, and also with Mundet, different cases. Each group was a rather sort of involved situation. But so this statement was conjecture in a paper in 2006 with Peter Cotton and with Steve Bradford and Peter Cotton. And so this was proved in my work with Olivier Bicard and Roberto Rubio. And so what is the beauty of this kind of theorem? So in particular, this theorem detects new invariants, new topological invariants that are hidden in the story. For example, if you take the group sp2nr, like, for example, for n equals 1, this is SL2R, right? Then this group here for sp2nr happens to be GLNR, whose maximal compact is ON. And so now there are topological invariants that are the first and second Stiefel-Whitney classes. And so these new invariants that you bring to the surface via this Cayley correspondence actually are important in detecting, in sort of counting components. And in particular, this is exhibiting in many cases the fact that fixing the Toledo invariant maximal is not enough. There are other invariants. Okay. So, but more relevantly in relation to Anosov and discrete representations is that these also, like the Hitchin components, consist entirely of discrete and faithful representations. They are Anosov, right? This is proved by Berger, Yossi, Labrie, and Winhardt. And as in the Hitchin components that I didn't mention, this, the mapping class group of the surface acts properly, right? Like in the case of the usual Teichmüller space, that the mapping class group of the surface acts properly, and the quotient is the moduli space of curves of genus G. So these are all common features with the Hitchin components. And now the question that that one would like to one asks is whether there are other groups besides these split and Hermitian families for which this phenomenon happens, for which there are special components, meaning that they consist entirely of discrete and faithful representations, and they are not distinguished by the primary topological invariants. So for a long while, it was believed that many, maybe I should say of us, believed that these were the only two families, but it turns out that that's not the case. And a new class of groups was detected, and these are the groups SOPQ. And so in joint work with Aparicio, Bradlow, Collier, Gotten, and Oliveira, we actually found that for this group, SOPQ, there is, on the one hand, once you fix the primary topological invariant, there are components that, for each value of the invariant, you do have a component in which the Higgs bundle can be deformed to a Higgs bundle with vanishing Higgs field. So hence these representations, the ones that can be deformed, I mean, the ones when you can deform to a maximal compact, so Higgs field equals 0, excuse me, those correspond to representations into the maximal compact of SOPQ. But then we found that there exist other exotic components, other non-empty components that are not distinguished by the primary invariants. And this we found by a construction similar to the one that I just shown for the Hermitian case, that there was some kind of Cayley correspondence, and that identified these components, this union of components, in terms of another moduli space that was now a moduli space of Higgs bundles, but now with a twisting of a p power of the canonical line bundle for this group, and then a bunch of holomorphic differentials. Right? So this is like a mixed situation of the split case where you only have this holomorphic differentials, or the other extreme situation, the Hermitian case where you have something like this where P is 2. Okay, so a combination of the results that we had in this paper with recent results of Guichard, Laborie, and Binhard, and Bader and Pozzetti on something called positive representations that I will come in a few minutes, prove that these special components consist also entirely of discrete and faithful representations. So the main goal of the rest of this talk, by the way, Jesus, how much longer do I have? We started
on the clock, 14 minutes, including questions. Now, that said, I don't have anything else to do afterwards. I mean,
okay, sure. No, I just
you can extend a bit, yeah, but people may start dropping.
No. I will stick. I just wanted to see where the discount minutes that, because we're starting a bit later. Anyway, that's fine. So the main goal of the rest of this talk in the remaining 13 minutes or so, or less, is to give a classification of the Lie groups for which special components may occur, and general Higgs bundle parameterization of these components. So in fact, the question is whether there are other groups. And so somehow the goal is to actually answer this question completely, right? And so this is the rest of my talk is a joint work with Steve Bradlow, Brian Collier, Peter Gotten, and Andre Oliveira that we put in January this year in the archive. And there, the key ingredient to answer this question and to do this classification is considering certain nilpotent elements in a simple Lie algebra, complex Lie algebra, and the corresponding SL2 triples. So let me explain. We call this magical nilpotents. I never liked this name, and at the end of the talk, some alternative name will be apparent to all of you. And I am just leave for you to see what is this new name that one should give. And so the thing is, we consider a simple complex Lie algebra, and G is a connected complex Lie group with this Lie algebra. And recall that an element is called nilpotent if the adjoint of it, this Lie bracketing, is an nilpotent endomorphism of the Lie algebra, right? So then we have the nilpotent cond in the Lie algebra, and G acts on the nilpotent cond by conjugation with finally many orbits. And there is a particular orbit that is a dense orbit, is called the principal orbit. These nilpotents there are called principal nilpotents. And so there is a relation given by the Jacobson-Morozov theory that every nilpotent element, E, can be completed to an SL2 triple. So this, you can find elements in the Lie algebra. So if you give me E that is nilpotent, you can find another nilpotent element and an element H that satisfies the Lie bracket relations of an SL2 Lie algebra, right? And so there is the Jacobson-Morozov theorem says that there is a bijection between isomorphism classes of nilpotent elements and isomorphism classes of the SL2 algebras that are spanned by these triples, right, in the Lie algebra G. So this is very fundamental. So once you have a nilpotent, you have this SL2 triple, we call SL2 triple here, and the triple generates an SL2 algebra. So if you give me one non-zero nilpotent, right, and you have the corresponding SL2 algebra, then the thing is that I can find two different decompositions in the Lie algebra G. One is given by studying the representation of SL2C in this Lie algebra. So this is just purely representation of SL2 in particular in a Lie algebra G. And so this is the decomposition in the WG, where WG is the direct sum of G copies of the unique J plus one dimensional irreducible representation of SL2. I mean, this is classical theory or representations of SL2 that I'm sure most of you know. That's one decomposition as an SL2C module. Another decomposition is that we can obtain a Z grading, yeah, decompose G in the direct sum of GJ, where GJ is defined as the elements in the Lie algebra that have eigenvalue under the action, the adjoint action of H given by J, right? And so this, in this decomposition here, the nilpotent element E passes from GJ to GJ plus 2, and the F from GJ to GJ minus 2. Okay, so let me just say that combining these two decompositions, right, and considering the highest weight subspace in WJ that happens to be the intersection of WJ with GJ, is giving the highest weight subspace when I study representations. This is completely characterizes the representation. The fact is, at the end of the day, I do have a decomposition of the Lie algebra like this, in terms of this highest weight subspace is Vj, right, where for the action of this nilpotent F, different powers, right? So these Vj's somehow generate the whole Lie algebra by the action, nilpotent action of the action of F. And so then with this in here, I can define a vector space involution, right? So that I call sigma sub E, and is a vector space involution of the Lie algebra that is defined by a linear extension of the following map. On V0, I decrete identity, and on these other pieces, I define it like this. You can check this is, it's an involution, vector space involution of G. And something very special happens for some nilpotent elements and the corresponding triple. And this is that sometimes this vector space involution is a Lie algebra involution. And when that happens, you call this element of the corresponding triple, you call it magical. And the good thing about that is that once you have this involution of the Lie algebra, by Cartan theory, you can actually associate it to this. There is an anti-holomorphic involution. This is an antilinear involution. That is a real form. So this element E defines canonically a real form, yeah, of the Lie algebra G, GR, right? So first theorem of my work with my collaborators is that a real form, GR, is such that this real form arises as the canonical real form of a magical triple if and only if you are in the following situations. The group is a split, the group is Hermitian of tube type, the group is locally isomorphic to SOPQ with this P bigger than 1, or locally isomorphic to this real forms of these exceptional groups, E6, E7, some real forms, E6, E7, E8, or F4. And these real forms are characterized by the property that geometrically, the symmetric space defined by these real forms are quaternion Kähler manifolds. So we detect, we knew about somehow these three, so we're not surprised that we have these three families, but then we have these other families. And This list here coincides precisely with the classification of groups admitting a positive structure given by Guichard and Binghard. I will come to that. But so the fact is that a real form GR arises as a canonical real form of a magical nilpotent if and only if the group GR admits a positive structure. I will come back to that. But now, let me just, I will go very quickly through this because I don't have time. But the fact is that out of a magical nilpotent element or a magical triple, I can extract like some Lie theoretic yoga, right? More information. And this more information are basically some integers, right? Some integers, mi. I won't explain, but I don't have the time, but just some integers, of which one particular integer is play an important role that we call MC. And then we extract another on the G0. This was the piece G0 in the grading that I defined before. There is also a real form of that. So we extract this information. And so here is the theorem that if E is a magical nilpotent element with corresponding canonical real form GR, if GR is a Lie group with Lie algebra, this GR, then there exists a union of connected components in the moduli space of GR Higgs bundles that, that I call H sub E, that have nowhere vanishing phi, and so no representation there.
I have very bad news. Uvori has given a fire alarm and I've been told to leave the building.
Okay.
So I'm gonna leave this on, but you may need to close this by yourself if I'm not allowed back. Or maybe I'll try to connect from the iPad from the street. Okay.
Okay. So if you want, I can continue.
You continue. You continue. You don't worry about it.
I'm sorry about this, Jesus, but I will be very rigorous on the time. Okay. Sorry about that. So I hope nobody else has.
No, you keep going. I think I can connect from the street. It just occurred to me. I think
okay, good. Jesus,
okay, bye.
Good luck. Bye. So the thing is that by this construction, we can find this a union of connected components of the moduli space of GR Higgs bundles that have nowhere vanishing Higgs field. And so these are, there are no representations which factor through a maximal competent group. And in fact, this union of components can be parameterized by this moduli space. Remember, I told you that there was an integer MC, so this is a moduli space of Higgs bundle twisted by this power of K for this other real group that we call the Cayley partner, right? And some holomorphic quadratic, some holomorphic differentials that are determined by these integers. It was the Cayley data that we extracted before. So the above parameterization is given by a map that we construct from this moduli space here and this holomorphic differentials into the moduli space that we call the Cayley map. And we prove that this map is an isomorphism on of its image, which is open and closed. And so then the defined components, right? We call this Cayley components. And so this map recovers the Cayley correspondence for Hermitian groups of tube type and for SOPQ, but also, and this is somehow a new different perspective to the Hitchin construction, it recovers also the construction of the Hitchin components in the case of the split case, in the sense that the Hitchin section that he constructed is actually a Cayley correspondence. So in that situation, one has this, there is no, this part of the correspondence, this with MC is not there, and we only have a space of holomorphic differentials. And so the Hitchin section is just a particular case of a Cayley map, right? And this is done with the principle a nilpotent element, a principal nilpotent element, which happens to be actually magical, right? So just to finish here, let me come back to this notion of positivity that I mentioned. And the notion of positivity on a real Lie group requires a choice of a parabolic subgroup P. And this is a theory that has been developed by Guichard and Winhard, generalizing notions of positivity by Lustig and in the case of split groups, for example, and some other notions that exist in the Hermitian case of tube type. And I cannot get into any details, but just say that a notion of positivity gives you, in particular, allows you to define a notion of positive triples in this flag variety. There's a flag variety, and so if you have a positive structure in GR, a P positive, you can define some order, some positive triples in here. You have 3 flags, and you can say when they are positive, a set of 3 flags. And so, so this is I just said, and for example, in the case of SL2R, and you take just the only parabolic that you have there, and then this flag variety is just the circle. The triple is positive if it consists of pairwise distinct points. And so with this in hand, with this notion of a positive structure on GR, you can define that a representation of the fundamental group of S in GR is P positive if there exists a raw equivariant map from the boundary at infinity of the fundamental group, this is just a circle, right, into this flag variety that sends positive triples in RP1 to positive triples in the flag variety, in this generalized flag variety. And so in a recent paper that actually appeared in June, Guichard, Labourie, and Winhard prove that if you have a group, GR, some simple group with a P positive structure, then the set of, first of all, positive representations are anosov in the sense that Labourie had defined, and so then they are discrete and faithful. And the set of P positive representations is opened in the character variety. This was actually known already, because I put it here for completeness. But more importantly, they prove that the set of P positive representations is closed not in the variety of representations, but actually in the subvariety consisting of representations of the fundamental group that do not factor through a parabolic subgroup. And so it so happens that in our work, we actually proved that we proved the following, that in this union of components, these Cayley components that I defined you previously with the Cayley map, this generalized Cayley map, in particular, this contain positive representations because one can put the whole Teichmüller, the usual Teichmüller via the magical inclusion of SL2R in the group. And then because the positivity is open, then there is an open set of positive representations there, right? And we prove that the representations corresponding in those components, in the Cayley components, do not factor through a parabolic subgroup. In other words, what we proved is that combining the results of Guichard, Labourie, and Winhard, and this result that the Cayley components consist entirely of positive representations. So I think since Jesus is already here, I can perhaps finish here.
Okay, thank you very much. Thank you. I was a bit distracted for the last
I'm sorry about that, Jesus. Yes.
Apparently, well, it's not your fault. It's theirs. They decided to run a drill, which is ridiculous because there was an actual alarm earlier on today. Okay. Any questions or comments? No. Okay, let me see if I can recover my thoughts.
If you don't have any comments, I can.
I actually have a comment. So when you say in this theorem that there is an open subset of possible or positive representations,
Yes.
is it open in the Euclidean sense, or is it like dense?
Well, this is the point. Is more than dense. Is open, right? Is an open. I mean,
no, but by
this,
I mean, you see, for me, open can be either open in the sense of balls or open in the Zariski sense.
I understand. Actually, if you look at the statement, right? So there is on the one hand the character variety of representations, right? And in the other hand, the moduli space of Higgs bundles. And these are homeomorphic, and there we are considering the usual Euclidean topology, right? Not the Zariski topology. And but the fact is that this is because of openness, we do have just some little chunk that is put there by taking the usual Teichmüller component in SL2R, and because of the embedding of SL2R in GR, even by the magical triple, we have something there. We should that is in there, and because of the open property, then we have an open subset. But the crucial thing is that now, and this was hanging for a while, is the fact that this is also going to the previous transparency, that in the paper of Guichard, Labourie, and Binhar, they prove almost that is closed here, except that they prove it's closed in a certain subspace of here, consisting of representations that do not factor through a parabolic subgroup. But we do prove that those representations of us do not factor through a parabolic subgroup, and therefore it's also close. And then it's a whole component. Is this so it's more than dense, it's actually the whole component, right? But let me just add one thing, that in fact the original conjecture,
oh, so you have several components.
Yeah, we are constructing by this, so our Cayley construction gives a construction of all these higher tabular components, right? This is the conclusion. There is a subtlety, that is that the original conjecture of Guichard and Labourie was that the set of p-positive representations is actually closed in the variety, not without any restrictions on this condition on not factoring through a parabolic subgroup. But also at the same time that there was the paper of Guichard, Labourie, and Binhar, there was this paper by Bader and Pozzetti showing that actually that is the case in the case of OPQ. But in general, there is, so now to conclude the story is that in general, there could be some, so the question is, are these Cayley components that we construct using Higgs bundles, all the possible higher tabular spaces that you can define in this context? Now, the answer is yes, except that there is the possibility for the quaternionic examples of some exotic components, but this would be ruled out, and this is believed that will not happen if this result of Bader and Pozzetti is proved also for the other quaternionic cases, or by other means, like just by inspectioning these exceptional groups, and as we do typically using Morse theory, you can rule this out, and it's believed that that will be ruled out by either of these two methods. So the conclusion is more, you can say that this construction that we give in terms of a Cayley correspondence gives a construction of all possible higher tabular spaces in the story. And it gives a parameterization, that meaning that using the complex structure on the curve, okay?
Okay, cool. Any other question or comments? No? Okay, well, thank you very much.
Thank you for your invitation.
And yeah, thanks a lot. See
Okay.
you around. Bye bye.
Okay,
Bye.
take care. Bye bye.